All right, so this is confidence intervals for population proportion and population mean. Okay, so I actually kind of like putting these both sections together because they're pretty similar when it comes to it. So it's I like to put stuff together always. Once you go to one section, it's very easy to go to the other. Really, the only difference between this section and the other section is pretty much two things, and we'll talk about that in a little bit. One of which is just an equation. The other one is just a little minor detail as well. Okay, so I just go over this when it comes to it. All right. So when it comes to a confidence interval, the best way I can explain what this process and what this concept is all about is, let's suppose you want to figure out um, the population proportion of people who like M&Ms in your county, right? Just want to see how many people do actually like M&Ms in your county. So what you want to do is you go out, you talk to people, and you ask them, do you like M&Ms? Yes or no, right? It's a simple question. But the problem is, right, you can't ask everybody in the county. So you can you go out and let's say you ask 100 people here, 100 people there, and 100 people somewhere else. But again, right, that's not the entire population of your county, but that's a small sample, right, when it comes to it. So what you want to do now is once you do that, you want to see, okay, given that those samples and you put them all together, so out of a total of 300 people, you want to figure out how many people said yes and how many people said no. So let's suppose 85% of the people said they like M&Ms in your county. So out of the 300 people in your you surveyed, 85% said they like it. So what you do is, well, based off that conclusion is, well, we want to figure out from there, does we can estimate, well, if I literally did everybody in the county, what percentage would actually like M&Ms? Okay. And that's what we're talking about here is, given a sample or two, varied pieces here and there is, well, just from there, can we, make an interval where if we actually really blow it up and ask everybody in that sample, would it actually be in there or not? Okay, so that's what we're actually talking about in this kind of situations as well. Just given a sample or two, given that portion, and now can we do it for everybody, in the same United States? Okay, another example is, let's suppose, people you're running for mayor or actually governor. Let's say governor for let's say California, for instance. And it's okay. So you want to figure out how many people are going to vote for you. So you go to different counties again, correspondent, and just ask them, right? So there's California is a pretty big state, so you can't just go ask everybody in California. So you go the same thing. Okay, oh, here, 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 and it's okay. So from these samples, approximately 50% to 55% of people will going to vote for you. Okay, so what you do is, okay, based off those counties, okay, you want to figure out, okay, if I make it to a larger scale to the entire thing of California, approximately how many people are actually going to vote for me when it comes to it. And that's what we're going to be doing here. Like I said, right? Given a simple sample, how do we make it, in broad terms when it comes to it? And most of it's going to be pretty straightforward. Some of it's a bit more complicated, as you know, but it's a small little example of what we're going to be dealing with here. Okay, is again, it's just given a sample, how do we do that into the general population? So overall, is it always going to be between here and here? Things like that. So hopefully it kind of makes sense, right? What we're going to be doing, and that's the basic core of what happening is when it comes to this kind of sections. Okay, so when it comes to finding these portions, right, or finding this basic portions, is the first definition we're going to talk about is something called a best point estimate. Okay, so a best point estimate is a single value is used to approximate the entire population parameter. So our best point estimates are going to be p hat, what represents proportion, well, for proportion, x bar for mean, and s for standard deviation. So these are the three ones we're going to be estimating for the entire population itself. Okay. Now our population parameters, so the ones we're actually be estimating, is going to be p for proportion, mu for mean, and sigma for standard deviation. Right. So these are our population parameters. So we're going to be using these to estimate that. That's the whole concept of this kind of stuff here. Okay. So to do so, we have the next definition called a confidence interval. So a confidence interval is the range of values used to estimate the true value of the population parameter. So the confidence interval is known as CI for short. So basically what we're happening is, since we're not actually asking everybody in California for a vote, is okay, it's going to be between here and here for sure. That's what we're trying to figure out. Somewhere between here. I don't know exactly, but it's somewhere there. That's what a confidence interval is all about. It's going to be estimating one value and it's another value. So we're going to pick two values somehow, and it's going to be in there. Okay, that's what a level of confidence is going to be. Okay? Now, the next major thing is very important is how confident you actually are it's between there, right? So if you're only 30% confidence between, that's not very good, right? But if you're like, almost 100% confident, that's very accurate. It means, you got almost as little error as possible when it comes to it. And that's what a little confidence actually corresponds to, is a confidence level refers to the percentage of all possible samples can be expected that can be expected to include the true population parameter. For example, suppose all possible samples were selected from the sample proportion, and the confidence interval were computed for each sample. So a 90, in layman's terms, in other words, right? A lot of information, but in layman's terms, a 95% confidence level implies that 95% of the confidence intervals would include the true population parameter. Or in other words, you're saying, okay, 95%, I'm 95% confident it's going to be here, which means gives you a 5% error that's not going to be in there, right? Because we're not picking everybody in the world or everybody in your sample, there's always that error bound when it comes to it, things like that. And we're going to talk about later on when it comes to, businesses, trials, and stuff like that, where they use a lot of this stuff as well. It's pretty interesting stuff, okay? Because again, we always have that error because of a human error when it comes to it. Okay, so now essentially the whole goal is to find this confidence interval instead of guessing what the range will be. So again, I don't want to guess. It's people are going to vote for me roughly between here. You can find exactly now using this type of method. So in order to do this, we need to find the cutoffs. In other words, what it's going from here to here for sure, right? It's going to be bounded between two numbers. So we got to find those two numbers when it comes to it. Now, the interesting thing is it's actually only done in one single number, which is nice. And that's something called the margin of error. Okay, so the margin of error is essentially saying if someone else did this exact same study, so if someone else did the exact same, asked different people, but did the exact same process you did as, asking, how many people would vote for you, would they get roughly the same result? Okay, that's what's happening here. So that's what a margin of error is. The margin of error is from one person to another person doing the exact same um, experiment and getting almost identically the same results. Okay, that's the best part. So that's what a margin of error comes into play when it comes to it. Now, this is one of the most important things on constructing a confidence interval, and this is the difference between the observed sample parameter and the true population parameter. This is how we will create our confidence interval by adding and subtracting the margin of error to our point estimate. Okay. So the whole process of this entire thing we're about to do is literally finding this number. That's the most important thing to finding, because from there, by definition, all we're going to do is add and subtract to a population estimate. It's either p hat, mean, or standard deviation. So before we actually do stuff, a little bit of information. So before we start finding the margin of error, what we're going to do is identify which distribution we're actually going to be using. So for our case for these sections, it's going to be proportion, which is P, and mean, which is mu, right? That's a population parameters we're going to be dealing with. Now the good news is when it comes to constructing confidence interval for population proportion, so percentages, um, probabilities, areas, right? Those are all proportions, right? The three P's are all the same. We're going to be using the normal distribution. Okay, so quick little fact, right? If you guys go to your formula sheets, whenever we're dealing with population proportion, we're using z-scores, right? The normal distribution curves, all of this stuff we did in the last chapters, right? However, when it comes to mean, however, so when constructing confidence interval for population mean, we're going to be learning a new type of distribution called a student t distribution. Okay, so it's a new type one. Now the good news is this is very, very similar to a normal distribution curve, which is the best part. Okay, so in our case, the way this t process is very similar. The only difference is this hump is far more dramatic. That is it. That's pretty much one of the only major differences when it comes to the shape of the curve. So 0 is still in the middle, right? So it's still very symmetric when it comes to it, things like that. So a couple properties we'll just write down. First thing, it's symmetric, right? Just like the normal distribution was as well. Okay. Now, here is the only difference between a t-value and a z-score. Now, if you guys remember a z-score, right? So the marker on here, so a z-score gave you area to the left of that value, right? And we use our table to find out. However, a t-value, so these are the t-values instead of z, so a t-value gives you area to the right of it. That is the most important difference between z-scores and t-values, which means, unlike the other one where a z-score means you're shading to the left, this one you're automatically shading to the right of the t-value, like that. Meaning we'll never give an area to the left. It's always going to be given to you area to the right of it. That is the one major difference between normal and t-values. Okay, so next thing is, how do we find a t-value using our charts, right? Because, everything else is going to be done for us when it comes to it. Now, this actually isn't that bad. It's actually a little easier than when it comes to normal distribution. To define a t-value using a format sheet, we need two things. The first thing is called an alpha, okay? So it's a Greek letter, alpha, like a little fish, okay? Now, to find this, your alpha is always equal to 1 minus the confidence interval asked of you. So 1 minus like 0.99. So in this case, for instance, if it was a 95%, we would go 1 minus 0.95, right, when it comes to it. And the second thing is something called degrees of freedom, or DF for short. So degrees of freedom is always n minus 1. In other words, your sample size minus 1. Okay. So in the next video, we'll talk about how to actually create or actually, find t-values when it comes to it, right?